Greetings of the day, one and all. I am Dr. Shanti Visalakshi, MCA Faculty of Hethraj College for Women, Chennai, Tamil Nadu. I am the participant of first short-term course on e-content development conducted during 13 December 2021 to 19 December 2021, which is duly organized by UGC Human Resource Development Center, Gujarat University. Today, we'll have a discussion over combinational circuits from the broader domain digital computer fundamentals. With the case study of adder circuits falling under the same category combinational circuits, let's try to get the better clarity. The prerequisite knowledge expected is one should have a knowledge about basic logic gates and its functionality. Basic logic gates are AND, OR, NOT and XOR. And the functionality associated with AND is for all ones it will return 1. For a single 0, the gate will be producing 0. Coming to OR gate, for all ones and along with every single one will produce the output as 1. Whenever all zeros, obviously OR gate will come out with 1. And NOT gate, it's a single input gate which will take one value as input. Correspondingly, it will be generating its complemented output. And coming to XOR gate, XOR gate is a special kind of gate where in which you can have the following functionality. For identical values, it will return 0. For alternate values like 0 or 1 and 1 and 0 combination, it will return 1. And also, we should know the need of combinational circuits. Combinational circuits, with the name itself, it is clear. Any combination of the basic logic gates can be taken to achieve the specific task. Say for example, a NOT gate plus and an AND gate, it will be producing NAND gate. So there we have taken the combination of NOT and AND gate. So the combinational circuits are nothing but we can have our own choice of basic logic gates for some specific purpose. So basically, what is the formal definition of this adder? An adder is a digital logic circuit. In other way, it's a combinational circuit in electronics that is extensively used for the addition of numbers. Addition of bits also I can say. So even with this adder combinational circuit, you can have some two types, half adder and full adder. There are furthermore adders are there, but then we are going to concentrate only on half adder and a bit of full adders. What's the difference between half and full adder is, half adder will be working with some 2 inputs, whereas full adder will be working with 3 inputs. So let's have a look over the functionality of an adder. So basically, half adder, it adds 2 binary digits. So whenever we have 2 binary digits for our case, we can expect the possible combination of 4. 2 part 2 is 4. So it starts from 0 till 3. So the combinations expected here, it's 0 and 0, 0 and 1, 1 and 0, 1, 1. The binary equivalent of 0 to 3. Okay. So this is the truth table which we have taken for the analysis now. So consider this truth table. I have taken. There are 2 inputs A and B designated for the binary values 0, 0 to 1, 1. Starts from 0 to ends with 1. And you have the sum value. What is the sum value? Let's check. So whenever we are about to add these 2 digits, 0 plus 0, it will be producing 0. And 0 plus 1, again can expect 1. 1 plus 0, it is 1. So long with 0 plus 0 and 0 and 1 and 1 and 0, there is no carry or extra bit generated. So what is happening? It will never be producing any carry. But coming to the fourth combination, whenever we are about to add 1 and 1, it will be generating the result as 1, 0 because 1 plus 1 is 2. 2's binary equivalent is 1, 0. So the least significant bit 0 will be taken for sum and the extra bit will be taken for carry, right? So on closely examining the sum output, we can able to narrow it down its functionality. It's simply an XOR gate. Coming to the carry value, have a close look over the truth values. It is 0, 0, 0, 1, which is nothing but the output of the AND gate. So one can realize a logic circuit for this adder is by incorporating an XOR gate as well as an AND gate, right? So two inputs, if whenever it is being supplied to the XOR gate, it will be producing the sum output. Again, the same two inputs, whenever it's been supplied to the AND gate, it will be producing carry, right? So the logic gate can be realized as this. Now I've taken an animated thing. For 0 and 0, the sum value is 0. For the same 0 and 0, the carry is again 0. For the next combination 0 and 1, it will be generating some value as 1 and there's no carry. It will be resulting with 0. And again 1 and 0, the sum output is again 1. There's no extra bit generated. So the output is 0. And then for 1 and 1, the sum value is 0, but the carry value or extra bit is 1, right? So what is the ultimate use of this adders wherever it is applied? It's like adders are always used to calculate addresses since because it is the main combinational circuit which is being used for addition. It can very well be used to calculate addresses and related activities. And even the table indices, even whenever the array is being incorporated, the data structures array has been incorporated, and even wherever it is required in the processor. Basically, one speciality about this addition operation is, according to computer based processors, this addition operation has got a significance because subtraction, the other operation subtraction, can very well be performed by means of additions through complement logic. That's a different topic then, but then whenever we are using complement logic, we can able to perform subtraction through addition. Okay, so the rest of the operations, as you know, the multiplication is repeated addition, whereas the division is repeated subtraction. So whatever it may be, the basic arithmetic operation, addition, subtraction, multiplication and division, we can perform it by means of addition itself. That's the power of addition operation with respect to processes. But then there are, even we have certain other limitations with half adders. So this half adders have no scope of adding the carry bit. So whichever bit is being generated as a carry bit, there is no mechanism to get added along with the other digits. So what we can do, we can take one more half adder, the carry in output or the extra bit output can be the input, one single input for the next half adder, right? So to overcome this, we ought to go for full adder. So because the real-time scenarios involve adding the multiple number of bits which cannot be accomplished using half adders. So it's a thing, it's like whenever we are left over with only 2 bits, it's well and good with half adders. Whenever we are about to add multiple number of bits, it's obvious to incorporate as much as half adders to be added along with, so as to make a move with the rest of the digits to get added. Right? So with this, we have come to the end of this presentation. So the materials which I have taken here is the references from this textbook and the web sources and certain other research articles. So at the outset, I would like to thank UGC Human Resource Development Center for having organized such a wonderful first online short-term course, and also for having selected me as one among the participants. Out of this short-term course, I have learned a lot, and it's been a wonderful opportunity for me too. And I feel like a privileged one, and whichever I have learned, I'll try to incorporate in producing or in developing further level e-contents. Thank you so much, organizers. Thank you, Professor Dr. Jagdish Joshi, for all your efforts. Thanks for all the subject experts and whoever is there, the technical support, or whoever is there behind the screen. Thank you all. Thank you so much. Thanks for the opportunity.